Assalamu alaikum, brothers and sisters. I'm Mahmoud. I'm doing a PhD in quantum computing, trapped quantum computing here at IQC. And I'm just here to talk about what exactly is quantum computing, why do we use trapped ions, and etc. Okay, so first thing. Oh, something's wrong, or even my hand. Okay. Can anyone spot this very tiny dot over here? Okay, so this very tiny dot is only one atom shining in the camera. And you might ask yourself, how could we even have only one atom suspended in the nothingness? And why would we even care about this? And also, like, we can have more than one atom, of course. We can have a chain. Something is wrong, okay. We can have a chain of atoms. And all of them suspended in the nothingness. And I'm basically gonna answer the question is, we use those to do quantum computing, okay? So first, what is quantum computing? But, okay, just before saying what's quantum computing, I just wanna say that the difference between quantum computing and the classical computing is basically that like quantum computing is not by any means gonna replace your laptop or computer or whatever. It's like the difference between a car and a plane. If you're just gonna go to the grocery store, you just wanna have like a car and just go. But it's not gonna be efficient to use a ferry, like to use a plane. But if you're gonna cross the sea, you might as well use a quantum computer. So, okay. Sorry? I hope our quantum computer flies someday, but okay. Okay. So what I'm gonna say over here is that by like theory, the classical computer or the normal computer we have faces what I would like to call a complexity wall. And why it faces a complexity wall is basically due to the fact that nearly all the classical computers basically check the solution one by one. The best you can do is that you can build a GPU that checks 100 solutions or 1,000 solutions one by one. But at the end of the day, it's just, and of course you can have a lot of sophisticated algorithms and everything. But like when you have a problem that is branching out, for example, if you have, for example, like this molecule over here. Can anyone recognize this molecule, by the way? It's caffeine. It's a lovely one. Okay, so this molecule is like had around like 100 electron, an active electron, I guess. So if you want to solve the problem for 2 electrons, you'll have a problem of, well, if you want to solve a problem of 1 electron, this is just going to be like a two level problem, or like two variable problem. Add 2 as another electron, it's just 4 variables. As another electron, just 8 variables. So basically, with these kind of systems, if you want to fully simulate this, and by fully, I mean like not using averages, like fully simulate the system, you will find the problem grows exponentially with time, or like with the complexity of the problem. So this is basically the complexity wall. Okay. I swear something's wrong. Okay. So, fair enough. Okay. Okay. Does anyone here like have a theoretical computer science background? Okay, so this is for you and only for you. This diagram you already know. We have the P space, the N and P. Basically, the quantum computer identity over all of those is not really recognized yet, but we know that it solves some NP problems. We know that it contains all the P problems, but how exactly the interaction is still like a research question. Like how exactly this is for like probabilistic quantum polynomials. So how exactly it lies, this is like a more of a fight.
I think P should be inside.
Yeah, it should be inside. Sorry. Yeah, exactly. Okay. Okay, so one good thing quantum computers can do is simulating the quantum nature itself, right? So, and why this is good, or like how can we use this? Like the direct thing we can use is to simulate molecules for drug delivery. Like I'm guess a lot of you knows, like, you know, like if you want to make a drug, this drug basically couples to like this drug has like a certain structure, and it couples to the protein or like to the protein that causing the disease. And if you find the right combination of the key, which is like the molecule you're trying to simulate with a quantum computer, and the protein, which is matched to each other, then voila, you find the drug. It's not as simple as that, of course, but this is just to say the framework, okay? Okay, so the question here, why the quantum computer works at this point, right? What is so special about quantum computer that makes them work? The answer to this could be whatever in the slide, or it could be like the quantum computer itself relies on the true nature of the material. So if you are trying to simulate something which is quantum by itself, simulating it using quantum mechanics is a better solution than trying to simulate it using normal computers or because normal computers is just a very special case of quantum mechanics that's not really the ideal situation. But what really gives the quantum computer their power is basically two properties, the superposition and the entanglement. Basically, the superposition is, in classical computers, we either have, if we have a bit that represents everything, it's either like a 0 or a 1. However, in quantum computer, the bit could take any other value. So it could take 0, it could take 1, it could take any other thing in between. You can see through this fancy picture that, it could be 1, it could be any other point on both spheres. So we have a special bit. We call it a quantum bit or a qubit. And if you concatenated some bits, so for example, if you concatenated 2 bits, you will have, basically the probability, you will have a superposition of the 2 bits being up or the 2 bits being down, or one being up, one being down, or the other way. So basically you have 4 possibilities now. So it's not about storing information, but more about the complexity of the system. And if you have 3 qubits, you can already see that, we have 0, 0, 0, 0, 0, 1, up to 1, 1, 1, which is 8 coefficient of the same of 3 bits. So the more qubits you have, the more basically coefficient you will have to do to describe the state. So imagine that you have 300 qubits. This is 2 to the power 300, which is a very unimaginable number. It just some people say that this is more than there is atoms in the universe, and just yeah. So this is the very first thing giving quantum computers their properties. The second thing giving quantum computers their property is something called entanglement. And entanglement is it's just a controversy between physicists up till now, but basically, I would say 2 particles are entangled if they are somehow correlated without having anything to be there is no reason for them to be correlated. So for example, if I take 1 electron here in Canada and 1 electron over there in Egypt, and I measured 1 electron to be up, the other one has to be up also. How they communicated, how do you know that the first one was up and this one has to be up? We don't know, but you can see over here, this is 0, 0, and this is 0, 1, but over there, you wouldn't find the 0, 1 and 1, 0 coefficients, basically. So yeah, entanglement is just something that allows you to put a very complex relationships between the variables in your system. Okay, that's it. How? So we talk about qubits. Let's get back to how can we actually build a quantum computer? Well, there is a paradox called quantum computers that the qubits is a very shy object. It's just any tiny heat disturbance or you can just lab in the middle of the lab and everything will get disturbed. So you kind of want to isolate them. But if you think about it, if you isolate the qubit, how would you interact with it, right? What would be the way? So, and also we want something the qubit itself, we want something to be quantum mechanical, right? So if you're gonna do a quantum mechanical qubit, we want something to be quantum mechanical. So those two questions: what is the qubit, and like how to isolate it, and then how to interact with it. And this is what I'm gonna answer right now. So first of all, what is the qubit? It's a very complex diagram. It's intentionally complex. The qubit is basically the atom. The atom itself is like the most quantum thing we have. It's just already like all of the physics was just developed to things like know what's like the atom and then structure and everything. And I would just want you to forget all of those graph and just focus in these two levels. So basically, if you know like atoms have energy levels, and if there is like an electron on the outer shell, this electron could be in one level or the other. And if it's in, for example, this level, we will say, oh, it's in zero. It has the state zero. If it's in this level, we'll say, oh, it's in one. And we can just do the superposition and everything. So, okay, so we have our qubit. It's the atom or the ion, but we'll get into this. Okay. Okay, so this is not the correct slide order, but okay. For some reasons, I will get into, we would like this atom to be ionized. So the first thing we do in the lab is that we shoot a laser towards the atom to make it an ion. And an ion is just an atom without one or more electrons. So we have an ion. And then let's get back to this picture. If I have a positive charge, which is my ion, and I have an electrode, which is like also a positive charge, they will repel, right? A positive charge is repel. So what if I make this ion between two positive charges? They will be repelled from the other side, right? So what if instead of making two, let's make it 3D. So I will make two electrodes positive here, two electrodes positive here, two electrodes positive here, right? So I will get something strapped in between, right? But unfortunately, this is not how physics work. And basically, if to do what's over here, you will see the ion strapped between all of those positive electrodes. You'll see it's just tripping. However, if I made two positive and then two negative and have the ion in between, but make the two negative alternate with the two positive, I can get an effect like here. So basically, now we have a rotating saddle, which basically this is how we would like to trap our ion. So this is the best, this is really nice. If you just have an ion suspended in the emptiness with electrodes having their charge, their electrodes.
When you say alternating, do you mean alternating current, like the poles alternate?
Yeah, exactly. So over here we'll have a minus V cosine and minus V cosine. So basically, I will show it. It will come. Okay. So now we have trapped an ion, right? And I will show you the picture first. So you see over here, those are the electrons. You see, this is go positive and then go negative, as if you have a rotating saddle, which basically over there, right? Okay, so again, this is an ion suspended in the air. We know that air has a lot of molecules, and every molecule can just hit our ion and just leave it outside of the trap, right? So that's why we have a very high it's just a high ultra high vacuum over here. So we have all of those. So basically, this is the structure. This is the trap. This is the alternating current. We have it inside the vacuum, and this vacuum, if you wanna visualize it, it's 100 trillions less dense than the air we are breathing right now. This is 10 to the negative 12 bar. Okay, so it's almost as if we are just approaching there. We have the ion, which is the qubit. We have the trap suspended in the air, and we have the vacuum. And one last question is how we would interact with this qubit, right? So it's over there in the emptiness. You can put your hand, you can put a wire, you can just put everything. So the only way that you can interact with it is with electromagnetic field or laser. Okay, so how can we talk with the qubits inside this chain, or this chain of ions that we shine laser into those ions. So the correct picture will be like the difference between each and every ion is like around 4 micrometers. So we can have this laser precision. We can really direct the laser beam into one of those ions. So yeah. So and you will ask yourself, oh, I can just shoot a laser and that's how I do quantum computing? And the answer is yes, actually. So how exactly we would like to think about doing computing? This is the very like the simplest thing we can do. The simplest thing we can do is that we can do a NOT gate, which we will have a NOT gate or like an X gate in physics. So the NOT gate will just take 1 and make it to 0. And the way we can do it, it's let's suppose our atom starts over here, all of them starts at like 0. And I shine a laser for some time, it oscillates and gets like at 1, whatever, like just choose it. So basically, over here, you will see all the atom at 0. And after some time from shining the laser, they will reach 1. So, okay, so just forget about this picture. If I have an ion over here and I shine a laser, it will rotate. Like if it's still shining the laser, it will rotate. And then, like continue rotating, rotate and continue rotating. If I timed my laser to only just be on for like this amount, then I just made an X gate. And you can imagine if you can make an X gate, you can make all other kinds of gates, but that's a different topic. And okay, so that's how can we make gates. We can also make like 2-qubit gates, which is like equivalent to the AND, but that's also like very complicated right now. But at least we can make no gate. Very happy. Okay, so this is me just showing you how complex it is to generate those lasers. Usually we like this is our vacuum chamber. Over here is like the trap, and you can see like everything goes in, and yeah, it's just everything needs to be very well aligned. Okay, and finally, oh, go ahead.
Which class of laser?
That's a good question, and that's exactly why I have. Okay. I'm not sure really how to navigate this.
Let's leave the questions till the end.
Okay, fair enough. Okay. Okay, I will answer your question and do that. But okay, this is the very final, and this is actually a very good question. Okay, and the final thing we want to know how, like, at the end, was the atom in 0 or 1? Like, as if we are doing computations, right? Like, in a Turing machine, just, like, it writes all over the tape, and at the end, you get bits, right? So, any number you have, if you write a Python program, you write whatever program, it gets you at the end some just answer, which can be represented in binary, right? So, the representation over here is just if the atom is shining or not. So, like this is just an example of a binary answer for some algorithm we have done, which is okay, we like 4 of them is shining, it means 1, 1, 1, then 2 looks like they're not shining, 1 shining, and etc. So we also read, so everything is done via lasers, basically. And okay, and this is the end of my presentation. I'm sorry if I was, yeah, this is supposed to be room for questions, but for some reason it's here. Okay, go ahead.
So there are like many kind of like particles and other phenomena that exhibit quantum effects. What are you using atoms and not say photons? What's your use for that specific implementation or that specific how compared to some other?
Good. So trapped ions is not the only way to do quantum computing. There's like many ways of doing quantum computing, including the photonics. So there is photonics. There is like artificial atoms, like we call it superconducting qubits. There is the trapped ions. There is like many platforms you can just make a qubit out of. Why do we why you choose one over the other? There's like set of specs. One of them is like how much error you can, like how much error, what's like, for example, so basically you do a gate, you do a NOT gate, right? So this is a perfect NOT gate, right? But this is not a perfect NOT gate, right? So like those are like the specs you can tolerate, and also how many qubits you can fit into a system. So over here, the best trapped ion system has like 1,000 qubit, but like you can see other platforms have like 4,000, and yeah. So
for example, photonics, they also allow you to have quantum communication.
yeah, exactly,
So it's
exactly.
like many benefits. I mean, why do you specifically choose ion?
Why exactly ions? Because ions are like very clean, very like has a very high fidelity gates, and also they have like something called an all-to-all connectivity, which basically you can entangle any two ions in chain. So
Like general purpose.
yeah, for like you just this is basically a fight between people in the field, which quantum platform is better, but at the end, yeah, go ahead.
I'm just gonna say, we'll have 2 more questions and then take a break for Maghrib, inshallah.
Inshallah.
And then we'll be back for
2 more questions on his question about the laser. Okay,
Sure.
go ahead.
We'll take it outside for a fight or what?
I don't understand why entanglement is useful, because as far as I know, you can't use entanglement to transfer information with cause and effect.
Yeah, you can't use entanglement to transfer information. It's a theory for like no communication theory and no cloning theory. Yes, of course. But to represent deep connection between, for example, 2 particles that's really happening over those caffeine molecule, those particles themselves are entangled like in the very level, in the very deep level, right? So basically entanglement allow you to like to have like a very complex relationship between the variables. So if this doesn't answer your question, I can just say without entanglement, we wouldn't have quantum computers at all, actually.
Gives it more degrees of freedom.
I actually don't know.
Good question.
Okay, good question. Go ahead.
Why is it an issue if you add more qubits? What happens to the system? Why is it harder to like?
Good question. If we have this is a trap, right? And the end of the day, this trap ends, right? So the trap, if you have the profile for the trap, you will see like the potential is just gone and then getting up. If you're very far at those two's end, like the ion will not even like there is no trap anymore, right? So that's one aspect. Another aspect is that you cannot, it's really hard to engineer a system, even if you can trap hundreds of ions. It's really hard to engineer a system that's that can like address those ions very efficiently. Like the best technology is that you move those ions and trap, like you'll have like like this trap would be like a very large trap, and you shuttle the ions to do operation on. This is basically IonQ if you are interested about which company does this.
Take 1 more question.
Go ahead.
Not sure if this is answered by the answer that you gave to somebody else, but if you are manipulating and using entanglement within the process of your qubits, how are you preventing, if the atoms are, and if we don't understand the process of entanglement between particles completely, how do you account for particles being entangled in a way that you aren't trying to account for? It's not something that you wish to manipulate between
Oh, okay.
preventing byproducts of entanglement that you don't wish to have, essentially.
Yeah, that's a good question. So this is actually one of the specs that you will measure how good the quantum computer is. So how much you are able to suppress those unwanted effects. But like to like if I want to have a very detailed answer, it will just say that we can have this, like the laser itself we are applying. We will have this laser, not just applying the laser, we'll have a very complicated sequence of laser pulses to make sure at the end of our entangling operations that we actually have everything not entangled back again.
That you're maintaining the
Yeah,
states
yeah.
that you want to have.
Yeah, exactly. Okay, so one thing, I'm sorry, one last question. So I just want to get to the one slide. If you can help me, I would really appreciate. One over before this one. Okay, yes, this one. Okay, so to answer your question about the lasers, so you see, when you say which kind of lasers, we basically have a lot of lasers we can do a lot of operations on. So for this transition, we have like 2 lasers, which is like 355 nanometer lasers to, for example, do this flipping. to cool the ion after it has been like in its location, we just have another laser. We just have many other lasers anywhere. So, and those calculated and defined based on the amplifier structure of this ion. And that's it. Thanks.
Okay, Jazakallah khair. Thank you so much.